This is AB Calculus test number 3, free response, problem number 1. We had a test last Thursday. It's an icy morning, and I intended to go over this in class today, but due to having this channel, I'm able to do this right now so you can see it, everyone. And what we have is a table. At the beginning, we have hours in one column. Below that, we have acceleration, hours ranging from 0 by 1/10 of an hour all the way up to 1 hour. An acceleration in meters per hour, and we have the text below. A heavy train initially stopped, begins moving. The table above shows the train's acceleration in miles per hour as a function of time measured in hours. We have let f of t equal the integral from 0 to t of a of x dx. A, use the midpoint Riemann sum with 5 subdivisions of equal length to approximate f of 1. And B, explain what f of 1 is and give its units of measure. So we have this train, and the train is going to be accelerating and picking up speed all the way up from time 0 to 1 hour. And we see the acceleration starts out at 90 miles per hour, and the acceleration decreases to 0, and so we don't have any acceleration after 1 hour, but the train has been picking up speed initially at these rates all the way up to 1 hour. So we're going to estimate, and this problem is one where if you can just sit back and realize our relationship between, now we've talked about for a long time now, position, then the next level below that is velocity, and the level below that is acceleration. And we're given acceleration. The table shows acceleration, and so we're going to try to find what f of 1 is. Well, if we're integrating, right, that's what this is, f of t equals the integral, we're going up one level. So without getting into any numbers, we can already answer part B, and that is the speed or velocity of the train after 1 hour. Now we know that speed and velocity are not exactly the same thing, but in this case, either one would suffice. We know that a train is only going to be going in one direction, so speed and velocity in this case are synonymous. So either one of these would be a correct answer in this instance. And now to find out what that speed or velocity is, oh, and I forgot units. In what? We had miles per hour, in miles per hour. And to remember that we're going in miles per hour, we're talking about a heavy freight train. That really helps us out. If we get some ridiculously high number in the hundreds for velocity, we know that probably hundreds of miles an hour, in other words, that's probably not going to be an accurate answer. Well, here we're given asked to find 5 subdivision and a Riemann sum, and in AP Calculus, we're asked to do 2 kinds of estimates of integration, one of which is the 3 types of Riemann sums. So I'm going to go ahead and just list these just kind of as a review. Riemann sums. We have a left Riemann sum, left, a right Riemann sum, And we have what we're being asked to find here, or used here, as a midpoint. And depending on, okay, 3 midpoint. And then we have the trapezoidal sum. And that's going to stand by itself. Okay, that's, but each one of these types, so 1, 2, 3, 4 types of things. For the Riemann sums, we're looking at rectangles of a width. In this case, we're asked to find 5 subdivisions. So if we take 1, which is, we go 0 to 1, 1 hour. If we take 1 hour and divide that into 5 subdivisions, we get 1/5, or 0.2. So each interval is going to be 0.2 in extent. So we go between 0, interval 1 is going to be between 0 and 0.2. Interval 2 is going to be between 0.2 and 0.4. That's interval 2. Interval 3 is going to be between 0.4 and 0.6. Interval 4 is going to be between 0.6 and time equals 0.8. So interval 4 and interval 5. The last one is going to be between 0.8 and 1. So we have our 5 subintervals. And so to write this, we're going to say approximation. Sometimes you use estimate of. Okay, we'll have 0 to 1, not 0 to t. We're going to have a of x dx is going to be v of t. Okay, that's going to be v of t, which is our velocity of t, which equals, we're going to put in 5 subdivisions. 1, 2, 3, 4, 5. There we have our 5 subdivisions, and each one of these subdivisions has a width. These rectangles has a width of 0.2. Okay, 0.2, 0.2, 0.2, 0.2, 0.2, and the midpoint for this first interval is going to be, we have 90, 90, 90. The midpoint is going to be a 90. The next interval is 90, 80, 78. Well, it's going to be 80 is our midpoint. Next one we have is 78, 80, 60. We're going to have 80 here as well. And this one here, this fourth one, our midpoint is 40. And our last one here, our midpoint is 10. And so this right here would suffice as our 100% correct answer. And boxed in red. And if we didn't put a number, I think it ends up being 60 miles per hour. But you can just leave this in this form, and that'll be sufficient. Now we get to part C, which a lot of you had trouble with. Assume the acceleration is constant on the interval from 0 to 0.2. How far does the train travel during this interval? Include units of measure. Show how you arrived at your answer. Well, what you have is we can make a little sketch of a graph here between time. In time, we're going to have 0.1 hours, 0.2 hours, and our velocity, well, we know that if we, after 0.2 hours, how far do we go? Well, if we go up here to where we put in our Riemann sum, right, our first thing, 0.2 times 90 we know we're going to be going 18 miles per hour. This is going to be in miles per hour here after 0.2 hours. And if acceleration is constant, which we're given the condition that it is, then our average velocity is going to be 9 miles per hour. Okay, so we have our average velocity, which is 9 miles per hour, times the total time, since 0.9 was our average velocity. Well, how far did we travel? Well, if we have 9 miles per hour times 0.2 hours, all right, we're going to have a cancellation, hours over hours, so we have 9 times 0.2, which is going to be 4.5 miles. That's how far we're going to go, and that will be our answer to part C. Anyway, I hope you did well on this problem. I'm going to box in this one too, which are answer units. And I'm going to try to prepare another problem, probably weather related. That's going to be similar to this one, where you have to just step back and look, consider what's going on. And the problem shouldn't be too hard. Obviously the mathematics, the arithmetic of this problem, that isn't too hard. And I hope the logic shouldn't be that hard either. So good luck, stay warm, and thanks for viewing.